Next, exercise 21. In this one, we are given a permutation sigma which permutes the letters in the English alphabet, all 26 of them, in this way. That is, each letter is sent by sigma onto the one that appears directly below that letter in this display. We have to write sigma in cycle form, that is, we have to find all the disjoint cycles of sigma and then write sigma as a product of those cycles. So let's start our but before, let's just write sigma in cycle form is this. So we start with the first symbol, of course, the first letter A. The image of A under sigma is H. So our cycle starts like this, and we will continue to use commas to separate the symbols, just like we have been doing. Although not using commas will not create any confusion here because we are not dealing with numbers, but let's just be uniform in what we are doing and continue to use commas. So image of A is H, image of H is M, image of M is P, that of P is R, image of R is S, image of S is then again A. So we have come back to this. Let me just see once more. A goes to H, H goes to M, M goes to P, P goes to R, R goes to S, and then S again comes back to A. Then we of course take up one symbol which has not appeared in this cycle. You can in fact take any symbol, but let's just be somewhat uniform and take B. Image of B is D, that of D is G, that of G is C, and C again is mapped back onto B by sigma. Now what would have happened if you took D, if you started this same thing with D? Actually nothing will change. What you will then get in place of this 4 cycle, this 4 cycle. But note that this 4 cycle and this 4 cycle are actually the same permutation. Here also image of B is D, image of D is G, that of G is C, and that of C is B. So you can in fact write a single cycle in many different manners, but you have to keep the cyclic arrangement same. You cannot change that cyclic arrangement. You can in fact start with G or with C. You can do those things. Okay, so A, B, C, D. Next E. Image of E is J. That of J is L. L goes to N. N goes to F. We have to continue from here. N goes to F, then F goes back to E. When we are writing a solution, it's as far as possible try to maintain that you write a cycle in one line. Here however, because of lack of space, I am writing like this. Okay, so E, F, G, H, I. Next, I is unchanged. I is not affected by sigma, so we write I. If you want, you can not write I also, because usually we do not write one cycles. The convention is that if the set on which your permutation is acting has some symbol that does not appear in the cycle form of the permutation, that just means that those symbols are unchanged by the permutation or are kept fixed by the permutation. That is the that's what we mean by not writing them. Here, however, we have decided to show it. Okay, so I, the next j is already here. ijk, image of k is O, and image of O is again k. So this is a 2 cycle. ijk l m n o p q. Image of q is u, and image of u, I think, yes, it is again q. This is another 2 cycle. p q r s t. T is mapped onto w by sigma. W goes to v, and v again goes back to t. So this is a 3 cycle. U, v, w, x. Next, x. Image of x is z, that of z is y, and image of y is x. To be sure that we have in fact considered all the symbols, let's just count the letters. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 26, 23, 26. So yes. So this is the cycle form of sigma. Next, 22. Let alpha and beta are, if alpha and beta are disjoint 2 cycles, what are the possible? Okay. If alpha and beta are disjoint 2 cycles, what are the possibilities for the order of alpha beta? To figure this one out, we are going to use the fact that disjoint cycles commute. Since alpha and beta are disjoint, we have this: alpha beta is equal to beta alpha. Also, since alpha comma beta are 2 cycles, so their squares equal the identity. These are things we already know. Hence, Now what will happen if we take the square of alpha beta? It really means alpha beta, but here that beta alpha in the middle can be now written alpha beta. So this becomes alpha square beta square. This is equal to identity. So the square of alpha beta is identity. Now if alpha beta itself is not identity, then that will prove that the order of alpha beta is equal to 2. So now suppose alpha beta is identity, then alpha is equal to beta inverse, which is equal to beta, since beta is a 2 cycle. We know that the inverse of a 2 cycle is the cycle itself. In fact, that is coming also from here. That fact and this equation, this one and this one are equivalent. If one of them is true, then so is the other. And in fact, there is no need to again write a justification for this. We already know this. We already know where this is coming from, which contradicts the hypothesis that alpha and beta are disjoint. They are not just unequal, they are in fact disjoint, which is much stronger than not being equal. So our supposition is wrong, i.e. alpha beta is not equal to identity. So that is why 2 is the smallest exponent, which makes this power equal to identity. Thus, the order of alpha beta is exactly equal to 2. Next, 23. Show that if H is a subgroup of Sn, subgroup of Sn, then either every member of H is an even permutation. is an even permutation, or exactly half of the members are even. Okay, so that means we have the symmetric group of degree n Sn in which H is a subgroup. Then either H is, H has only even permutations. That is, H is a subgroup of the alternating group An, or if H has odd permutations, then exactly half of the permutations are odd and the other half is even. That's what we have to prove. If all the elements of H are even permutations, then there is of course nothing to show. So assume that H has some odd permutation. Say sigma. Sigma is an odd permutation that is in H. Okay. For any even permutation tau belonging to H, the product sigma tau is an odd permutation and is in H. So if we find any even permutation tau in H, then this product, because we are taking the product of an odd permutation sigma and an even permutation tau, so the product will be an odd permutation. This we already know. One more thing we know is that because H is a subgroup, it's closed, so sigma and tau are both in H, so this product will be in H. So this means what? This means that every even permutation in H is giving rise to an odd permutation again in H. Let's just write that. So every even permutation in H gives rise to an odd permutation in H. In particular, the even permutation E, the identity permutation is also an even permutation, that in H gives rise to the odd permutation if you take E in place of tau sigma in H. So that means the odd permutations that we obtain from even permutations in H include sigma in them. Okay, so now the situation is this: you have H, you take an even permutation tau in H, sigma is fixed, okay, you then get an odd permutation sigma tau. So you vary this tau over the set of all even permutations in H, you get as many even permutations you have in H, that many odd permutations in H you get. But is that true? Will different taus give rise to different sigma taus? Next, that we have to see that. If tau 1 and tau 2 are distinct even permutations in H, then sigma tau 1 and sigma tau 2 are distinct odd permutations in H. Why? Because if you suppose that they are not distinct, then you use the left cancellation law in the group, because after all we are in the group Sn, right? So this will imply tau 1 equal to tau 2, contradicting their distinctness. We have chosen them to be distinct even permutations. We can write within brackets by the left cancellation law in Sn. So there are as many odd permutations in H as we have even permutations in H that appear in this manner. But can there be more odd permutations in H which may not appear in this manner from even permutations? Let's see. Next, let mu belonging to H be any odd permutation. Then mu is equal to sigma tau, that means sigma inverse mu. Okay, then sigma inverse mu is an even permutation in H such that sigma inverse mu is equal to mu. So that means all the odd permutations in H in fact appear from some even permutation tau in this form. That is, you multiply that tau by sigma from the left side, you get that odd permutation, and for this arbitrary odd permutation mu, that tau which will give us this mu by through multiplication by sigma is sigma inverse mu. Let's see these things, that whatever we have written here actually makes sense. Sigma originally has been taken to be odd. Okay, so sigma inverse will also be odd. Why? Because if sigma inverse is even, then it belongs to the alternating group. No? Then its inverse will also belong to the alternating group, which is nothing but sigma, but then sigma will be even. So that is why if sigma is odd, then sigma inverse is also odd. So here we are looking at a product of two odd permutations. One of them is sigma inverse and the other one is mu. So that is why this is an even permutation. And because sigma originally comes from H and now our mu comes from H, so by the fact that H is a subgroup of Sn, sigma inverse mu is not only an even permutation but it is in H. And that is why this is an even permutation in H that gives you mu. So all these things ultimately tell us what? It tells us that the elements in H can be divided into two parts. One of them contains all the even permutations and one of them contains all the odd permutations. One of these odd permutations is sigma, and what we have shown first of all is that every even permutation gives rise to an odd permutation through multiplication by sigma. Okay, so that way we have got odd permutations, many odd permutations. What then next we showed is that different even permutations give rise to different odd permutations. So this is a one-to-one injective function. There is no collapse. Okay, two different taus will not give us the same sigma tau. That's why there are at least as many odd permutations as there are even permutations. But then we also additionally showed that nothing is left out. I mean, in this process of finding odd permutations from even through sigma actually takes into account all the odd permutations, and that is why there are exactly that many odd permutations as there are even permutations. So half of H is even, the other half is odd. That we have been able to show that now. So we just simply write, so exactly half of the elements of H are even, or let's just write permutations also. And this completes the solution. Okay, next. (24). Suppose that H is a subgroup of Sn again. Suppose that H is a subgroup of Sn, but now additionally this is given of odd order. There are an odd number of elements in H. Prove that H is a subgroup of the alternating group An consisting of all the even permutations of Sn. So it is given that H is a subgroup of Sn and H has odd order. We need to prove that H is a subgroup of An. Suppose H is not a subgroup of An. That means we don't have just even permutations in H. There is at least one odd permutation in H. Then H has at least one odd permutation. But what we saw in the previous exercise, either all the permutations in H are even or exactly half of the elements in H are even permutations. But then by the previous exercise, or if you want to write more elaborately, by the result in the previous exercise. Exactly half of the elements of H are even permutations. But half of the elements of H are even permutations means, among other things, that half of the elements can be made and can be considered. In other words, H should have an even number of elements, because then only half of it will make sense. No? But this implies that H has an even order, which is a contradiction, because it's given that H is of odd order. So that means our supposition is wrong, and hence H must be a subgroup of the alternating group. That is H must be a subgroup of AN. This completes the solution, and let's just do one more. This one is not difficult. Give two reasons why the set of odd permutations in Sn is not a subgroup. Odd permutations in Sn is not a subgroup. The odd permutations in Sn don't form a subgroup because one reason, of course, is that the set is not even closed. Not closed in the worst manner possible. I mean, it is as not closed as possible. You take any two odd permutations, their product is not in the set of odd permutations. Their product is always even. The product of any two odd permutations is an even permutation. And another, you can take this, the identity permutation E is not odd, it is even. So you can have these two reasons. Actually one is enough, but we can in fact you can just show one of these as the reason why the odd permutations in Sn do not form a subgroup. So let's just end this video here itself. In the next Gallian group theory video, we will continue with the other exercises which come after this. And now after this we have this ring Gallian video. So see you in that.